This video is all about evaluating limits analytically. The previous video was about evaluating limits graphically and numerically, but now we're going to be presenting sort of like shortcuts or theorems that we can now use in order to, instead of making a chart every time or instead of making a graph every time, to see and observe what our function is doing at around a certain given x value. What we're going to be doing is using a direct substitution method. And the direct substitution method can be used in only certain situations, and we're going to be identifying those. Here were two different type of limits that you could try to evaluate. And one thing that you may have noticed when we were doing the graphical or numerical way is, well, why couldn't I, when looking at this graph, just say, okay, as I got closer and closer to 1 from the left and right, so as I was observing the x value 1 and I was approaching that from the left and right, what was the y doing? Well, it was getting closer and closer to 2. So our limit is 2. That's the value it's approaching. You'll notice over here these graphs are almost identical, and you could say the same thing even though there is a hole there. Right? So I want to mention this because in this situation you could have said, hey, you know, I can just plug in 1 into this function and I would get my 2. Over here you don't have the luxury of doing that because there was that something goofy happening there. So direct substitution could have been used here. Direct substitution could not have been used over here. And so what we're going to be doing in this 3.3 section, or analytically evaluating limits, is trying to figure out, alright, when can I use direct substitution, such as something like that, and if I can't use direct substitution, is there any modification that I could do so that I could use direct substitution? But for now, for this lesson, for this video, we're only going to focus on when can I use direct substitution. So 3.3, evaluating limits analytically, this is our goal. So my class has the luxury of discussing and developing these properties. These are some basic limits. These up here are some basic limits that you're always going to want to keep in the back of your mind. You're going to remember basics are the base. We start there and we can build on from there. So if you don't have the luxury of sitting in an awesome class with awesome peers who are willing to discuss this and develop these, then you're going to have to kind of take the time to develop these ideas and make these basics strong so that you can grow off of these. These right here are properties as well. You're going to want to get a firm understanding of those. Make sure that they make sense to you. Here is just one example that we did. Let's look at the function f of x equals 4, for example. Okay, and then let's look at this limit of that particular function as x approaches 2. The thing we would have done before is we could have done a chart, okay? And we could have approached that x value 2 from the left and the right, and we could have said, all right, what's it doing as we get closer and closer to it from both sides? And what you'll notice is that they are always approaching 4 because it's a constant. That's the nature of this. If you were to graph this, it's a constant. It's just a line that will always maintain the y value 4. So you're going to see that as we approach it from the left and right, yeah, there's no change here. It's just going to be those y values are constantly 4. Alright, so we came up with this theorem and we were able to check it out with our textbook. So this right here is kind of abstract, but you can see, try any constant. Try any function that's a constant here. Try 10, try 12, but you're going to see that same pattern occurring no matter how you look at it. So that right there, I mean, in class we developed this concept right there, as well as this basic limit and this basic limit as well. So that's what I mean. Try to just play around with these basic limits. Make sure that they make sense. Alright, so let's do a problem. Let's actually start to work with these. So like I said, every move that you have should have a basic limit or some sort of property behind it. So what I'm going to start to do here is, this is kind of a longer, it's a polynomial, it's a longer polynomial occurring with scalar multiples, there's powers involved here, there's constants. So I'm going to break this apart. the first thing I'm going to say is, well, we do have this property that we've learned and discussed today that you can, this is the sum and difference rule, that if you have two functions going on and the limit of two functions being summed up, you can split them up. You can split them apart. So I'm going to do that. Plus, all right, here's my other function. We could have called this f of x, could have called this g of x. And so I'm going to split this up now and say the limit as x approaches 2 of 3. Okay, so I just use this rule right here, that property. All right, another thing that I can do is I'm going to now, you can see this chunk right here, it's a combination of a scalar multiple and also it has a power. So you'll notice right here there's a power going on, and I'd like to get myself to that, but I'm going to get rid of the scalar first by using this property. Any kind of scalar you can bring to the front. And once again, please play around with these. Make sure that it makes sense that you could do this. So as x approaches 2 of x squared plus, and then the limit of 3 as x approaches 2. Alright, so now I'm going to go ahead and say this now I can use direct substitution on. Right here, I can go ahead, if I have a limit of a power, so x to some sort of number, then what could happen is whatever I'm approaching with x, I can stick that value in for that function, and I can calculate. So here I'm going to take this c and I'm going to plug that into my function. So this is one of those cases where yes, you can go ahead and just sub this in. So I'm going to get 4 times 2 to the second plus, right here, this is what we just kind of explored. It's this basic limit right there that you can go ahead and say that if you have the limit of a constant, it's always going to be that constant. Okay, it's just going to be 3. So now you can just evaluate this. It's going to be 4 times 4, so 16. Oops, yeah, 16 plus 3. All of this is equal to 19. There's your answer. All right, let's look at another one. This is number 18 in the homework. So I'm going to start out with looking at this quotient, and you're going to ask yourself, for limits, can I just go ahead and calculate the separate limits of the numerator and the denominator? And yes, you can. We do have a property that states that you can do that as long as this bottom does not equal 0 if you were to plug in that x value. And it doesn't, so I'm going to go for it. We have limit of our numerator and then divided by the limit, as x approaches 3, and then the limit as x approaches 3 of this function right here. Okay, so now this, you can look at this a couple of ways. This is a radical. If you want to, you can rewrite this. I'll go step by step here. As x plus 1 to the 1/2, right? Because you can write the square root, or any kind of roots, to a rational exponent. So we're going to do the same thing here. Or I'm sorry, we're not going to do the same thing. I'm just going to rewrite this. Alright, so now this is going to be using this property right here. If you have a function to any kind of degree, you can go ahead and just find out what is the limit of that inner function. So I'm going to go off to the side here, and I'm just going to calculate, well, what is the limit of that inner function? So what is the limit of x? What is the limit as x approaches 3 of x plus 1? And here you can go for using, once again, I'm going to check mark the ones that I'm using. I'm going to use the sum and difference, okay, and just take these one at a time. So the limit as x approaches 3 of x plus the limit as x approaches 3 of 1. And right here we can go ahead and just use this basic limit that you can directly substitute in that 3 for the x. So we have 3 plus, and then here's another constant, it's 1. So I'm going to evaluate what is the limit of x plus 1 as x approaches 3. Well, it's just going to be this. It's right here. It's 4. So now I'm going to use this property and say, alright, it's going to be 4 to the 1/2. So this is all equal to, on the top, we have the limit of x plus 1 to the 1/2. Basically what we're seeing is we can directly substitute in here. We're going to get 4 to the 1/2 all over here. The more you practice this, the quicker you're going to see it, but I am going to write it out. We have the limit as x approaches 3 of x minus the limit as x approaches 3 of 4. Sum and difference once again. And then up at the top I'm going to evaluate this. This is just 2. At the bottom we can use that direct substitution basic limit right there. It's going to be just 3 minus, and then we have this once again constant 4. So all of this is going to be 2 over -1. We get our -2. Okay, so that's number 18. What I want you to take out of this is that for every single step that you do, you're going to start to see the patterns of where can I use direct substitution. And the more you do, the more quickly you'll come to the realization that there's these certain types of functions that you can do that for. So here is a list of those types of functions, as I was saying, that you can use direct substitution for. Polynomials, basically that sum and difference rule, as well as the power rule that we saw, this one and this one, allows us to do this, that we can just directly substitute in for any polynomial. Rational functions that are not undefined. If you ever try to directly substitute in and you get a 0 on the bottom, that means that direct substitution cannot be used. And we'll be discussing those in more detail in the video to come. Composition functions, those as well, you can use direct substitution. That's, for example, if you have something like x plus 1 to the 1/2. That is a composition function. It's a function within another function. You have this x plus 1 going on, and then you take that x plus 1 and you raise it to the 1/2. It's where there's multiple functions going on. That you can also use direct substitution, and we also saw that with radicals. These kind of lead to each other. If you have the square root of x plus 1, for example, you could always rewrite that as a composition. Therefore, direct substitution can be used for both of these. All right. Here is the homework for that problem set. Give those a go. The biggest thing again in this lesson was to realize when can I use direct substitution, and it's using those basic limits that we were discussing, as well as the properties of limits. You're going to be wanting to really look at those and justify every move that you make. I can do this because of those basic limits or those properties.